It's time for your Chapter 11 bonus multiple choice review video. Number 1. Experiments on learning in animals sometimes measure how long it takes mice to find their way through a maze. The mean time is 18 seconds for one particular maze. A researcher thinks that a loud noise will cause the mice to complete the maze faster. She measures how long each of the 10 mice takes with a noise stimulus. What are the null and alternate hypotheses for the appropriate significance test? All right, so they believe that it should be 18 seconds. So I'm liking choices A, B, and C initially for the null hypothesis, but for D and E, we always use the equals in the null hypothesis. So definitely not D, definitely not E. And then notice in the alternate for A, B, and C, it hits all the different possibilities. Is it not equal to, less than, greater than? And this is where I guarantee some people will mess up, is because it says that the researcher thinks the loud noise will cause the mice to complete the maze faster. But we need to think about, what does faster time mean? It means that the mice would complete it quicker than 18 seconds. So technically, we would have a less than 18-second scenario. So really, we would want option B. So remember, bigger doesn't always mean better. Faster doesn't necessarily mean a higher value. In terms of time, it technically means a smaller value. So always be on the lookout for just maybe the little bit of differences that some scenarios produce and how that could basically flip-flop your alternate hypothesis. Number 2, you were thinking of conducting a one-sample t-test about a population mean mu using a 5% significance level. Which of the following statements is correct? So option A, you should not carry out the test if the sample does not have a normal distribution. Well, that kind of sounds appropriate, right? But if you consider the times where we had to make a box plot of our data, we weren't looking for our data to be normal. We were just looking for it to not have strong skewness, and there could be some skewness present, right? So we don't necessarily need the sample to not be normal. B, you can safely carry out the test if there are no outliers. Oh, this is sounding good. Regardless of the sample size. Well, obviously we don't want outliers, but you got to consider, regardless of the sample size, we can carry out the test if there are no outliers. There were times where we could use the central limit theorem, and that would override the fact that there were maybe outliers present. So our data could have outliers, but if we have a big enough sample size, the central limit theorem just washes that all away. So I wouldn't say regardless of the sample size. Tricky. C, you can carry out the test if a graph of the data shows no strong skewness, regardless of the sample size. Well, this is going in the opposite direction, and this is really something that we haven't specifically talked about. But if you have a very small sample size, like less than 15, technically, besides no strong skewness, we also really can't have any like moderate or kind of a medium level amount of skewness. Like we can have slight skewness, but with very small sample sizes, no strong skewness, no bueno, and moderate skewness is still not okay. So this one doesn't work either. D, you can carry out the test only if the population standard deviation, sigma, is known. Well, that's not true. We could carry out a z-test if the population standard deviation was known, but we can still do a t-test when we don't know sigma. So that leads us to E. You can safely carry out the test if your sample size is at least 30. And that is going to work out here because if we have at least a sample size of 30, the central limit theorem is going to allow us to use that t-test procedure. So answer choice E. Number 3, a 95% confidence interval based on n equals 15 observations from a normal population is negative 0.73 to positive 1.92. If we use this confidence interval to test the hypothesis that mu is equal to 0 versus mu is not equal to 0, which of the following is the most appropriate conclusion? Ooh, all right. Now, we got to look at, they use different alpha levels here. They're doing fail versus rejecting the null hypothesis. And in this problem, it was about a 95% confidence level, which means the alpha level is the complement of the 95%. So the alpha level should be at a 5% level, not at a 10% level. So it's not going to be C, it's not going to be D. Now, do we reject or fail to reject at the 5% level? Well, we are hypothesizing about if mu is really 0, and is 0 inside the confidence interval. And it is. So can we reject a 0 if it is a possible population value? And no, we cannot reject it. So I would say the correct answer would be B. We cannot reject a mu equals 0 possibility because it exists in the confidence interval. Number 4, which of the following has the smallest probability? Now, this is about comparing, number 1, Z test statistics to T test statistics. But not only that, but also looking at different T test statistics with different degrees of freedom. Now, we got to remember about what the big differences were between Z distributions and T distributions. So we had said previously that Z normal distributions are always going to be the tallest and the narrowest. They don't have a lot of room on the outside. And all of these are going to be centered. Let's see if I can get a line down the middle here. Is always going to be based on a standard normal, which means the mean in the middle is going to be at 0. And notice all of these are saying greater than 2, and then we get less than 2, but they all focus on a value of 2, basically 2 standard deviations away. So let's say that's right here. Now, a T distribution, on the other hand, is going to be shorter than a standard normal distribution. And if it's shorter, it's going to have fatter tails. So at some point, it's going to cross over and look something like this, for instance. Okay? And so let's say that represents the degrees of freedom of 5. And so now what would degrees of freedom of 2 look like? Well, 2 would have to be even shorter than the 5. And at some point, it's going to cross over and then be the tallest in the tail ends here. So let's say that's degree of freedom equals 2. Now, whenever we focused and we said that it was, let's kind of first focus on A, B, and C here. We said greater than 2. Well, if you consider the tail end of the standard normal has that much area greater than 2 versus the degrees of freedom of 5T distribution is technically going to be more than the Z one. And then the 2 degrees of freedom from beyond 2 is even going to be more beyond 2 compared to the 5 degrees of freedom and the standard normal distribution, right? There's more area underneath that red curve than the purple curve than the green curve in those 3 situations. So which one has the smallest probability out of, let's just say, A, B, and C? Well, C has the smallest probability. But now let's look at what if we flipped the inequality around and did less than 2 in both of these situations? Well, less than 2 would mean we start at 2 and we go down all the way to negative infinity. It's all of that area. Well, that is definitely not a smaller probability. I mean, that creates much larger probabilities. They're going to be over 50%. So we should have automatically eliminated these last 2 options here. So I would say the correct answer is C. The standard normal is always going to produce the smallest probability. The smaller and smaller and smaller the degrees of freedom are, the bigger and bigger and bigger those probabilities get because those tail ends keep getting fatter and fatter and fatter. Number 5, a significance test was performed to test mu equals 2 versus mu is not equal to 2. A sample size of 28 produced a standardized test statistic of t equals 2.051. Assuming conditions for inference were met, which of the following intervals contains the p-value for this test? So they're not actually asking us to calculate the p-value. They just want to know if we did calculate it, where would it fall in between? Is it between 1 and 2%? Is it between 2 and 2.5%? Is it between 2.5 and 5%? Between 5 and 10%? Or is it bigger than 10%? Well, since our test statistic is positive, then if we wanted to calculate the p-value, then we would go greater than or equal to 2.051. We would use TCDF and start at that positive 2.051, and we would shoot up to infinity. With how many degrees of freedom? We would have n minus 1, so 27 degrees of freedom. So if I type that into my calculator, let me grab my calculator here. So second variables down to TCDF, 2.051, comma 99999, comma 27 degrees of freedom, and that gives me 0.02504 to 4 significant digits. And this is where people would be going, let's see, it's slightly bigger than that. So the answer's got to be C. But that's where some people are going to get in trouble, because they forgot to go back and look at the alternate hypothesis and see that it was a two-sided test. So technically, we need to double this one-sided p-value and create a two-sided p-value. So 0.02504 times 2 gives me basically a smidge over 5%, which now means our correct answer would be D instead of C. So if you forgot to double your p-value, you would have said C was the correct answer. But if you remembered to double the p-value because you checked the alternate hypothesis, and remember, if the alternate was less than or greater than, then we would just stick with this one-sided p-value. But since it was a two-sided test, we technically needed to double that p-value. Number 6. A study of road rage asked separate random samples of 596 men and 523 women about their behavior while driving. Based on their answers, each respondent was assigned a road rage score on a scale of 0 to 20. Are the conditions for performing a two-sample t-test satisfied? Well, let's consider here the conditions. So one, do we have random samples? We have separate random samples. Okay, well, that looks good. What about the independent condition? Can we assume that there are more than 5,960 men and 5,230 women? And I would say that's definitely true. I mean, this doesn't make it sound like it's only for like one town or, a small community. To me, this is acting like it's more on a national scale, or even if it was a state scale, it would be okay. So I think the independent condition is going to be okay. And then the normal condition, well, we have very large sample sizes. So central limit theorem is going to apply all the way here. So I'm feeling like the answer's got to be yes, right? So let's look at our answer choices here. Maybe. We have independent random samples, but we should look at the data to check normality. We don't need to check the data. We have large sample sizes for the central limit theorem. B. No, road rage scores on a scale of 0 to 20 can't be normal. Why can't they be normal? I mean, I would think we could calculate a mean from those scores. I think that's going to be just fine. And the scores themselves don't have to be normal, right? They could be skewed. But the CLT is what's going to allow us to verify the normal condition. C, no, we don't know the population standard deviations. Well, who cares? We're doing a T test, not a Z test in the end, so we don't need to know the population standard deviations. All right, D. Yes, the large sample sizes guarantee that both populations will be normal. Well, this almost sounds great because we got large sample sizes, but that doesn't guarantee that the population distributions will be normal. It'll guarantee that the sampling distribution will be normal. So I don't like that one technically. And then E, yes, we have two independent random samples and large sample sizes. Yeah, that fits exactly everything that we saw in that problem. So I would say the correct answer is E. Number 7. Scoot this over just a bit. There we go. Are TV commercials louder than their surrounding programs? To find out, researchers collected data on 50 randomly selected commercials in a given week. With the television's volume at a fixed setting, they measured the maximum loudness of each commercial and the maximum loudness in the first 30 seconds of regular programming that followed. Assuming conditions for inference are met, the most appropriate method for answering the question of interest is. So should we be doing a 2-sample t-test, a 2-sample z-test, a paired t-test, a paired z-test, or a 2-sample z-test for a difference in proportions? We're not doing proportions in this problem. Get out of here, E. You crazy. Now, I guess the main thing we first need to consider is this a paired problem or a 2-sample problem? And it kind of makes it sound like, again, it's a 2-sample, right? Because they're wanting to measure the loudness of a commercial and then the loudness following the commercial. But they're pairing those two things up there, right? So these 50 randomly selected commercials are paired with the normal, regular programming that followed that commercial. So this truly is just a 1-sample problem, but it is a paired example here. So it's not A or B. And they didn't give us a population standard deviation to consider, so we're just going to be doing our normal t-test instead of a z-test. So it's not D. So the correct answer in the end is C. Number 8. Oh, wow, we got a lot to read here. Let me scoot this over. There we go. Researchers want to evaluate the effect of a natural product on reducing blood pressure. They plan to carry out a randomized experiment to compare the mean reduction in blood pressure of a treatment, the natural product group, and a placebo group. Then they will use the data to perform a test of the null hypothesis that the difference in the means is 0 versus the difference in the means is greater than 0, where the T represents the true mean reduction in blood pressure and the P represents the mean reduction when they take a placebo. The researchers would like to detect whether the natural product reduces blood pressure by at least 7 points more on average than the placebo. If groups of size 50 are used in the experiment, a 2-sample t-test using a 1% alpha level will have a power of 80% to detect a 7-point difference in mean blood pressure reduction. If the researchers want to be able to detect a 5-point difference instead, then the power of the test would be less than, greater than, still 80%. It could be either less than or greater than 80%, or it would vary depending on the values of the population means. Now, talking about power, we said there were basically 3 ways to increase power. We focused on the first 2. The first 2 were to increase the sample size and to increase the alpha level. The third one we didn't really discuss a whole lot, and that's really what's happening in this problem. They are saying that the power is at 80% to detect a 7-point difference. Now, the null hypothesis is just saying that there is no difference between the two. So right now, the null is a 0 difference versus they want to detect a 7-point difference. And that would fall in line with the alternate, right? It is a greater than 0 difference. They want to detect a 7-point difference. But if researchers want to be able to detect a 5-point difference, then technically that 5-point difference is getting closer to the null hypothesis than a 7-point difference. So technically, by decreasing the amount between our alternate value and the null hypothesis, we are in fact reducing the power. Now, if they had said, if researchers want to detect a 10-point difference instead, well, that's getting even further away from our null hypothesis of a 0 difference, so then power would increase. So the farther away we get from our null hypothesis, the higher the power will be that we will correctly reject the null hypothesis. So in this particular instance, I would say the correct answer is A. The power is going to be less because we are reducing our difference here that we are wanting to detect. Number 9. Let me scoot this over. There we go. A researcher wished to compare the average amount of time spent in extracurricular activities by high school students in a suburban school district with the average time spent by students in a large city school district. The researcher obtained an SRS of 60 high school students in a large suburban school district and found the mean time spent in extracurricular activities per week to be 6 hours with a standard deviation of 3 hours. The researcher also obtained an independent SRS of 40 high school students in a large city school district and found the mean time spent in extracurricular activities per week to be 5 hours with a standard deviation of 2 hours. Suppose that the researcher decides to carry out a significance test of that there's no difference between the two means versus a two-sided alternative, meaning that mu sub suburban is not equal to mu sub city. Which is the correct standardized test statistic? So number 1, are we dealing with a Z or a T test statistic? Well, did they give us a population standard deviation? And I could very easily see some people go, well, yeah, look, standard deviation. But they didn't say those were the population standard deviations. They said those were the standard deviations based on random samples. Those are sample standard deviations. So we are, in fact, not doing a Z test statistic. We are doing a T. So it's either got to be C, D, or E. Now, the formula in general for a t-test statistic was the statistic, which in this case is the sample mean, minus the parameter divided by the standard error. But that's for a one sample problem, and this is a two sample problem. So we need to extend this out a little bit more, right? So we need to look at the difference of the sample means minus the difference of the hypothesized means divided by, and then this part you are given on the chapter test because it's on the AP Stats exam formula sheet. So you get the standard error portion of this. So I would honestly first focus my attention on this part. Does this match up? Nope, not with B. Does that match up nicely with C, with D, or with E? And I got to tell you, one of those definitely looks like a close match compared to the other. This doesn't look like it matches. This is getting closer. But ultimately, in the end, these are the only ones where they are squaring the sample standard deviations underneath that square root. So I am confident, without even checking the rest of the problem, that the correct answer has to be E. And the final one. Suppose that the researcher decides to carry out a significance test of the null hypothesis is, again, that we have equal means for suburban versus city versus that two-sided alternative. The p-value for the test is 0.048. A correct conclusion is to fail to reject versus reject. So we could first start our attention there. And let's see, they give us alpha levels of 5% in all of these. So if my p-value is 4.8%, that is technically less than an alpha of 5%. And I'm assuming that this p-value has already been doubled because of the two-sided alternate test. So I don't have to worry about doubling that number. So the p-value is less than the alpha. So I would reject the null hypothesis. So it's not A, it's not B, it's not C. So let's see. Both of those match up exactly in that first part, right? They reject because the alpha is less than, or the p-value is less than the alpha. And then are we going to state that there is or is not convincing evidence? Well, if we reject the null hypothesis, we would say there is enough. We do have enough evidence here. We do have convincing evidence that there really, truly is a difference. We would not use a not here because that would result from failing to reject the null hypothesis. So in the end, I would say the correct answer is E. All right, good luck studying for the Chapter 11 test, and hopefully these questions will pay off. Good luck.